Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Omer studied at the Weizmann Institute under Balazs Szegedy and a.k.a. Benjamini, and currently he's an assistant professor at the University of Toronto, and he's going to be with us until the end of the week.
Thank you. So I guess I should start by saying what the graph limits that I'm talking about are, or maybe having a quick poll of how many of you are familiar with the concept of the weak local limit, also known as the Benjamini-Schramm limit. So at least some of you are familiar, and okay, 1, 2, 3. Does anyone want me to say what it is? You want to hear it? Good. So, okay, so what is... So first of all, what is the local limit of a sequence of graphs? So we have some graphs Gn, and we have some xn, which is a vertex of Gn. It's a marked vertex. And we say that this converges to some limit graph G, which will also have a marked vertex of x. So this is the definition. If for every finite radius, the ball okay, so for a ball we need to say what graph it's in and what is the center and what is the radius. So let's say that the ball in Gn around xn of radius r converges to the ball in G around x of radius r. So what does this mean? So the ball is just a finite subset of the graph. It's all vertices up to graph distance r and all the edges between them. And this is a discrete set, and converges just means that it equals for large enough r. So this just means equal for r greater than some r naught. I'm sorry, for n. And equal means isomorphic as a graph with a marked vertex. So some examples, the usual examples that help demonstrate what this is. So one thing that you could think of is an n by n square of the lattice. So you also have to say what the marked vertex. So the marked vertex is also called the root. And we have to specify where it is. So let's say it's somewhere in the middle. So if you have something like this, then if you take a fixed radius, a ball of a fixed radius, and n is large enough, then you just see something that looks like the infinite lattice. And in fact, this converges to the infinite square lattice. Another example, we can take the same graph Gn, but we can put the root in the corner. So this is again a bit of the square lattice, and this time the root is in the corner in the nth graph. And this is going to converge. So if you take a ball of radius r here, then you see something that looks like a corner in the square lattice, and this is going to converge to something like this. It's going to converge to a quarter of the plane with the marked vertex at 0, 0. Another example is a binary tree. You can put the root at the top, and this converges to the infinite binary tree with the root at the top. So I'm not going to draw the infinite tree, but you all know what it looks like. So these are some examples. And this is, okay, so this gives you some topology formally. This gives you some topology on the set of graphs, and this is the notion of convergence in this topology. It's a metric topology if you want to think of it that way, but we're not going to need any of that. Okay, so this is the notion of a local limit, and what I will be concerned with is a weak local limit. And so what is the idea? So given Gn, we take Xn uniformly. So it's a random vertex in Gn. And once we do that, Gn and Xn gives you some distribution on rooted graphs, since Xn is not necessarily a given vertex. So this gives you some random rooted graph, and now you have a measure on rooted graphs, and you can think of a weak limit with respect to this topology for the local limit. So this is a distribution on rooted graphs, and we take a weak limit. And specifically what this means, so the definition would be is that Gn converges to some random graph, to some random rooted graph, and this will be a weak local limit. Now, when you take a random root xn in Gn, then the distributions converge to this distribution. If Gn xn converge to Gx, so this is in distribution. And again, there's a more concrete way of saying this, that for any radius r, you have some distribution on the balls of radius r, and you want this distribution. So this now is a discrete set, the set of possible balls of radius r, and you want the distribution on these to converge. So again, we can look at the examples that we have here, and this time you start with just a graph with no marked root. So if you start with a bit of the square lattice, an n by n square, and you take a weak limit of this, so you take a random root, and with high probability it's going to be far away from the boundary, which means that the ball of radius r is going to look like a piece of the infinite lattice, and it's still going to converge to the square lattice, to the infinite square lattice. If you take a binary tree up to depth n, then you don't get the infinite binary tree as before, because when you take a root at random, with probability half, you get one of the leaves. Half of the vertices are at the last level, and a quarter of the vertices are at the previous level. So in this case, what we're going to get is a graph that looks like this. So it's possible that the root is at the bottom. This happens with probability half, and then you get something which is this. So you have an infinite path going up from the root, and at each point along this path you have some additional binary tree coming down to the level of the root, but no further down. So this is what you get with probability 1/2 when the root is at the bottom, but with probability 1/4 the root is at the second level, and with probability 1/8 at the third level, and so on. So what you get is still you get always the same graph. You always get this this infinite tree, but the root is now at a random location with a geometric height. So this is an important note to understand, that when you take even a sequence of deterministic graphs, the weak limit is going to, in general, to be a distribution on graphs and not a deterministic graph. Now, in this particular example, you can say that the graph is the same and only the location of the root is different. But this is not, but in general you can get different graphs, and the easiest example is to take a graph which has two components, each has half of the vertices, and they look completely different. So you can take half of the vertices in a tree and half in a square, and the result will have, with probability half, you'll get a square lattice, with probability half you get this. Okay, so this is the weak local limit, and as I've said, it's also known as a Benjamini-Schramm limit. And the reason is the following theorem.
When Noam gave this talk under these names, David Aldous gave him a lot of shit and said these are bad names.
Yes, and David Aldous has come up with this no concept of a limit at some point, and yes, and Itai and Oded, I believe, came with this independently, but Oded can say.
He wants to call it differently. I forgot what he wants, but he doesn't like the weak local limit.
I think that's also what he was using, and
it's known called it's a weak distribution.
Okay, so there are several. This notion goes by several names.
He didn't sort of insist on who invented it; just insists that it's a bad name.
Yeah. So okay, so this notion. So several people discovered this notion over the years, and it's a fairly natural notion. So it's not very surprising, and it does go by several names. I'm going to stick with weak local limit, but if you strongly prefer, you can take your favorite video editing software and do a search and replace afterwards. So what is the theorem that the Benjamini-Schramm theorem in this context? So it says that if Gn are planar graphs and they have bounded degrees, so this means that all of them are planar, all of them have uniformly bounded degrees. I should say they all need to be finite. So for this concept to make sense, you need the sequence of graphs to be finite, although the limit in the interesting cases will be infinite. And Gn converge to some graph G in the sense of the weak local limit, and the root here is not really important, so I'll ignore it. Then G is almost surely recurrent. And this is in the sense that the random walk on the graph G is recurrent. So,
And it doesn't matter where you started?
yes, random walk is recurrent regardless of the starting point. That's true for any graph.
Yeah, but
Well, for any.
graphs, this is a distribution of graphs. but
Yes,
say
okay, it's true for. Yes, so the graph limit is always connected, and therefore it is always almost fully connected. But and so okay. So some comments about this theorem.
Wait, why is all this connected? What if I take?
Well,
what if I take sort of just my GNs are sort of more and more copies of a 4-cycle.
okay, so there are several ways you can define this, and actually, as I wrote it, the limit might not even be unique, but if you take several components in GN, then it doesn't really matter because the balls of any finite radius only see one component. So if you exhaust the component, then so if you have a lot of small components, then the limit is only going to see one of them in the limit. So essentially, the weak local limit says the following. So you take a random vertex x in G, and you ask what is the distribution on the neighborhood that you see around you. So the neighborhood is in the graph metric. So different components have no influence on the limit. So in some sense, it only makes sense to talk about the component of the root in the limit. So formally you could say that you take this limit G and you put some additional vertex that is not connected to anything, and as I wrote it there, it will still be a limit, but
throwing the assumption that you connect.
Yes, but you can just as well require that the limit has just a single component where the root is located.
Could have taken the lattice and the tree that something is specified before.
Okay, so if you take the lattice and the tree, then the limit, so you get a graph which with probability half is this tree, with probability half is the square lattice, but it is always connected. So you get a graph. So the limit is a distribution on graphs. The limit has half of the mass is located on the square lattice, half of the mass is located on this graph, but all of the mass is located is supported on connected graphs. Now, several things you can ask about this. So, first of all, how common is it that the limit actually exists? And this is relatively easy to answer, because if you have graphs with bounded degrees, then this is a compact topology. So you have only a finite set of possibilities for any given radius, and therefore it's a compact topology, so you always have subsequential limits. And so the assumption that the limit exists is not a significant assumption. It will hold for any subsequential limit otherwise. So there are two more assumptions here, the bounded degrees and the planarity. Now the bounded degrees is...
Compactness doesn't give you any information about rate of convergence. Just says that the limit exists.
Yeah.
So can you say something? Does people look into this and for nice families that for nice families of graphs, how fast you converge to the limit?
So in particular examples, you can frequently calculate this, and in many cases you can get explicit estimates. But really, it really depends on what examples you have in mind.
Can be as slow as you like in general sense.
Well, it's like, the interval 0-1 is compact. And so every sequence there has a convergent subsequence, but we don't ask how fast it converges.
In that generality, you can ask for, but except for a nice sequence.
Yeah. So for specific cases, you can ask how fast does it converge, and you can and usually you can get some estimates, but yes. Okay, so the bounded degrees is partly a technical lemma. So as I said, you need it for the compactness, but you can relax it somewhat and still have tightness, which will still allow for convergent subsequences. So it's enough to have some moment bound on the distribution of the degrees. And so it's possible to relax it in this sense. The theorem is only known for bounded degrees, and the proof uses the fact that the degrees are bounded in a couple of non-trivial places. So it's not, so you can't.
But there are no counterexamples?
Yes, but there are no known counterexamples of graphs with unbounded degrees, but yes, so that the limit exists and it's transient.
You mean planar with unbounded degrees?
Yes, planar. So
It's the same notion for bounded average degree, right? But say then we don't know the theorem.
yes, yes. So okay, so planarity. So all of these examples are planar, and indeed in all of these examples you can see that the limit is recurrent. Here it's the square lattice. Here you have this infinite tree, but actually it has just a single path going to infinity and finite things connected to it. So the finite things do not affect recurrence of the random walk. So as far as the random walk concerned, you can restrict 2 times on this path, and then you just have one-dimensional walk. So these examples are both recurrent. If you have something like a cube, an n by n cube in 3-dimensional lattice, then the limit will be the 3-dimensional infinite lattice, but this is also not going to be recurrent. But it's not planar, so it doesn't violate the theorem. But still, the assumption of planarity was suspected that this also can be relaxed, and in fact.
I have a question about the bounded degree thing. If you take, say, a binary tree with n, n vertices, and you add, from the top, from the usual root, you add, you make that also degree n.
So you just add something like this.
Right. Then when you choose the uniform vertex, it's going to likely to be at the top there.
Okay, so this
You
is.
can worry about the limit. The limit is blowing up at that point in various senses, but we also think of the limit being an infinite binary tree and one vertex.
Yeah. So there is a question of what do you want to assume? What is the topology and what is the family of graphs that you want to work in? If you have a finite second moment on the degrees, then the limit is guaranteed to exist and be locally finite. And in that case, the random walk makes sense on the limit. So if it's not locally finite, then things might be. Then you don't really need to take the binary tree. You can just take a star with a single vertex connected to n vertices.
You assume the second moment is bounded at every of what
Of the degree of a uniformly chosen vertex.
I see, so first moment is not enough.
Okay, so first moment is not enough to get a locally finite limit.
that is already enough.
The star.
Yes. Yeah. So in order to use the tightness that I mentioned, you need a second moment, or maybe one plus epsilon even. But so I think I would be willing to conjecture that at least with second moment the theorem will still be correct. But if the proof or counterexample is provided before dinner, yes. Okay. So the theorem I'm going to talk about, and this is with Balazs Szegedy. And it's pretty much the same except that we relax the planar condition. So if Gn converge to G and they are finite with bounded degrees, and have an excluded minor which I'll call H, then G is almost surely recurrent. So what is the excluded minor condition that we have here? Would anyone like me to define it?
Yes.
Good. So what is an excluded minor? So excluded minor is a bit similar. So a minor of a graph is a bit similar to a subgraph, but with a twist. So a minor, so you start with some graph G, and you're allowed to delete edges, and you're allowed to delete vertices. So this gives you a subgraph if you only carry out these two operations. And finally, you are also allowed to contract edges. So anything that you can create from G by using these operations is a minor of G. So contracting an edge just means that if you have the edge, then you can shrink it and the two vertices become a single vertex. So you get just one vertex where the edge was, and it's connected to the same neighbors as before. And okay, so this can create some irregularities in the graph. So if you have a triangle and you contract an edge, then you get a double edge. So you can have multiple edges created by this. And if you have a double edge and you contract one of them, then the second edge becomes a loop. So self loops can also appear when you take these operations. There's nothing in all of what I said that fails if you have multiple edges or self loops. So you can just allow them, and there's no problem. Okay, so this is
Any excluded minor?
okay. So what is an excluded minor? So
No, but the theorem is you choose any H.
yes. So the theorem is that if there is some graph H which is excluded from all of them, then the limit is recurrent.
Is it it's just excluded from the limit or from the G ends?
From the G ends. So a family of graphs G has an excluded minor H if H is not a minor of any of the G ends. So
this should work even if you take a family of excluded, family of graphs?
For the H? So for H of, yeah, so in general, if you require several excluded minors, you can just relax it to having a single one, and the theorem will, and this is sufficient for the theorem.
No. What if the even?
Yes.
What if the even G's have one excluded minor and the odds have nothing?
Okay, if in that case you have some sequential limits.
Or then each of them.
So you have some subsequence that has only one of them as an excluded minor. So in general, if the graph H is a large and complicated graph, then the theorem becomes stronger, since you have more graphs that don't contain it as a minor. Perhaps the most well-known fact involving graph minors is Grotowski's theorem about planar graphs. So it states that G is planar if and only if it has no K5 and no K33 as a minor. So K5 is a complete graph on 5 vertices, K33 is the complete bipartite graph. So in particular, by taking H to be either one of these two, then the original theorem also follows. In fact, what we actually prove is something slightly larger, slightly stronger even. So there is some condition on the family of graphs Gn that we require. They require that they have some common structure. And this is a common structure that families of graphs with an excluded minor are known to have. But in fact, we allow a slightly broader definition of the structure. So there are some families of graphs that our proof applies for them, but they do not have any excluded minor. And so far, I don't know of any combinatorial description that describes the families of graphs directly, the families of graphs for which our proof works. So excluded minor is a sufficient condition, but it's not the exact condition that we need. And what is the structure? So this is based on a theory for the structure of graphs with an excluded minor. This is due to Roberts, Seymour, and Thomas. And it says the following. So given a graph H, there exists some constant K, finite, such that any graph that doesn't contain H as a minor can be constructed by the following steps that I'm going to write, so that G with no H minor can be built by the following construction. So what's going to happen? We're first going to construct some building blocks, and then we're going to put the building blocks together in a prescribed, also by prescribed rules. So for the building blocks, the first thing is you take a graph G with genus at most K. So this just means that you can embed it on a surface of genus at most K with no intersecting edges. So K equals 0 would be planar. And the second step, you're allowed to decorate at most K faces with complexity at most K, and I'll say in a few minutes what this means, but roughly this means that you have a face on the surface, so the graph is embedded on the surface, and you have the faces, and within a face you can add some vertices which are connected to the boundary of the face in some way. And the complexity controls how you can connect it, how you can connect these new vertices to the boundary of the face. The third step, you can also add at most k vertices with any neighborhood. So you can add some small number of vertices, you can connect them to anything you want. And this gives you the building blocks for this family of graphs that we are going to use. And finally, in order to put the building blocks together, you take clique sums of the building blocks. So what is a clique sum? A clique sum, so a clique in a graph is a set of vertices with all the edges between them existing. And so you take two cliques of size at most k, and you identify them. So this just means that if you have one graph, let's say with a 4-clique, and you have a second graph with a 4-clique and anything else here, so you just take these two cliques and identify them, and you get a new graph with the original 4-clique as the intersection. And you can repeat this last action with as many building blocks as you want. So each time you take another one and you glue it onto the structure you have.
The less equal k is about the size of the clique.
I'm sorry?
The less equal than k is about the size of the clique.
Yes. Yes, so the size of the cliques is valued by k as well. Now, I should mention that this description, this structure theorem, is essentially equivalent to having an excluded minor, in the sense, so for any fixed h, there is some k, so that you can construct the graphs with no h minor in this way. But also for any k, there is an h, so that all of the graphs constructed in this way do not contain h as a minor. So it means that proving a statement for any family of graphs with an excluded minor is equivalent to proving it for any family of graphs that can be constructed in this method for some k. However, there are some differences in what we require, because actually we don't require everything here, and we can allow a little bit more than k vertices to be added in step 3, and we can allow as many faces as you want to be decorated in the step 2 of the building blocks. So the graphs that we can actually deal with form a larger family. So one example might be something like this. So you take the square lattice, but now in each square you add the two diagonals. So you can think of this as an n by n lattice, and adding the two squares in a face, adding the two diagonals in a square face is a decoration with a bounded complexity, with defined complexity. But you can't create a large graph, you can't create a large square like this using the rules as written there if you can only decorate a finite number of faces. But as I said, our proof allows you to decorate as many faces as you want, and in fact also some other places where k is finite the boundedness of the K can be slightly relaxed.
And we know there are graphs of this type with the decorations that have no excluded minors. You know, there are families of graphs after these decorations.
This one in particular.
Yeah.
So it contains everything. Contains everything.
Yeah, so if you take a large part of the square lattice of this type, then this will contain anything as a minor, and it's very easy to find a minor. So if you want, say, K5 in something like this, you just pick 5 vertices far enough apart, and you take paths between them. And if the paths are going to intersect, then you actually make sure that they do not intersect by using the crossing edges. And this gives you an embedding of this graph inside this decorated lattice where the edges are paths, but then you can just contract all the edges in a path to get a single edge. So this is a subgraph, and you do the contraction to get K5 as a minor. But you can get any graph you want as a minor of this.
In the structure theorem, you don't have anything about bounded degrees, right?
The structure theorem doesn't have anything about the bounded degrees, no. And okay, and I think to get the so I might need to add a 5th step here where you're allowed to delete some edges at the end. So obviously this is not going to make any problem, but it's possible that you glue things along a clique and then you delete some of the edges in the clique. So and this actually might be needed for the construction to construct any graph with no minor. So this is not an important point, however. Now I have some time to speak about the proof. What time do I finish, by the way?
We have about 20
Good.
minutes.
So maybe I'll start by speaking about the decorations. So there are several things that need to be dealt with in the proof. So one part is the graphs with a bounded genus, and then you need to show that these additions don't significantly change their recurrence.
I will believe you on the addition. Just tell us about the bounded genus.
Okay, so we can start with the bounded genus, and then you also need to worry about the sums and the things that you can create by taking the clique sums.
You don't bound how many times you can add this.
As many as you want. But again, we require the final degree to be bounded.
That's kind of a cut.
Right. So let's so maybe first I'll see how we can prove this for graphs with a bounded genus without any additions. So we have something very similar to the original statement by Benjamini and Schramm that graphs with bounded genus have recurrent limits, and so for genus 0 it's planar, and we want to prove almost same. In fact, we use the original statement for planar graphs, and the following lemma allows you to make the transition. So if a graph G has genus at most K, then there exists a set S in the graph. The size of S is at most some constant times the square root of the size of the graph, such that if you remove this set, you get a planar graph. Now, there are various ways to see this. One way is based on a theorem that if you have a graph with a bounded genus, then it can be separated. It has a separator of size of order square root of g. So in fact, it's possible to find some cycle in the graph so that if you remove it, the two halves each have size at least 1/3 of the original size, and the length of the cycle is something like square root of the size of the graph. So this constant might depend on k, on the genus. And once you do this, you're left with two graphs. Each of them has half the size, and each of them is on some surface. If you cut along the cycle, you get some surface, and the sum of the genera of the two surfaces is the original k. So you get things which have small. So either each of them has a smaller genus, or one of them is planar and the other one has the same genus, and you continue by separating each time. So the graphs get exponentially smaller, and the total number of vertices that you need to remove is not too large. So this is the first step, and
Wait. But if half of this is planar, then you have still the mu. You have removed more than square root of g.
And you iterate that.
so you have removed square root of g, and you have a graph which is at most 2/3 of the original one, and maybe has the same g.
Half of g.
No, you remove square root.
So because okay.
So the theorem is that there exists a separator of size or of square root of the size of the graph.
Oh, I see that.
Yeah, so the graphs get smaller exponentially, and the total things you remove don't grow up too much. Okay, so this shows that you can so what is the meaning of this lemma? It means that you have some small set so that everywhere else the graph is planar. And as I've said, the idea of the weak local limit is you take a random vertex and you ask what is it that you see around this vertex. And what I argue is that you're not going to see this set S. With high probability, if you take some fixed radius, with high probability you only see things that are in the difference g minus s, which is planar. So
If you remove the separator of square root, then you repeat the same thing in each of the parts.
So g is equal to g1 union g2 union with some small s. That's in a single state of separation. And the genus of g1 plus the genus of g2 is at most k. So either it's 0 and k, in which case one is planar and you need only to continue with the other one, or both of them have smaller genera, in which case, so this is an induction on k also, that's hidden here. So in this case, by induction on k, you can find the set in each of these.
But if one of them is planar, then you may have to add square root of g plus square root of g over square root of 2 plus j of e over.
Yeah, so you get a square root
square root of 4
n plus square root of 2/3 n plus square root of 4/9 n.
It's fine, okay.
It's still bounded, it's still over square root n. So okay, so we can find this small set, and what happens if we take a random vertex now if we take a random vertex x in G, and
Here you need the bound.
yeah, so let's consider the probability that a ball in the graph G around the random vertex x of radius r, let's consider what the probability that this intersects the sets S. So Okay, so for each vertex in S, the number of vertices at distance up to R from this set, so the degrees are bounded, let's say, by M. So for each vertex here, so if this is a vertex of S, there are at most m to the radius vertices inside this ball, or something like that. So you get at most m to the radius, or maybe radius plus 1 to account for the volume, times the size of S divided by the size of G.
So you seem not to need bounded degrees. You just need that the balls of radius R for each R have finitely many vertices.
Boundedly many vertices.
Yeah, well, balls of radius 1 give you the degree. So, yeah, so it's possible to. So in fact, we don't really need.
Balls of radius 1 would give you average degree.
Again?
Balls of radius 1 would not give you maximal degree, it would give you average degree, right? Because you're sort of averaging for X.
Yeah, okay, so what are you saying that?
So you might get a weaker condition than bounded degrees.
Okay, so it's possible to use, so for these parts of the proof, it's possible to use bounded degrees. The thing is that at the moment, the goal is to reduce the statement for graphs with bounded genus to planar graphs. And for planar graphs, we resort to the Benjamini-Schramm result, and there the bounded degree is used in a more fundamental way. So not. But it's true that for this reduction, you can use a weaker assumption than bounded degree. Okay, so you have something like this, which is at most some constant m to the r plus 1 divided by square root the size of the graph. And if the graph is very large, then this converges to 0, because the m is fixed and r is fixed, and this goes to 0 as the size of G goes to infinity. So this means that for any fixed radius, the probability that you see the set S when you look at a ball of radius R goes to 0. So what does this mean? So you can take, so suppose you have the graphs Gn, and you can also look at Gn without the set Sn, which is the same set for this set for Gn. So these things are planar, and therefore the weak limit is recurrent. These things are not planar, but the weak limit is the same as the weak limit of Gn minus Sn. Because for any radius R with high probability, you don't see. So this gives a bound on the total variation distance between the measures here. So this effectively reduces graphs with a bounded genus to planar graphs. So let me say some things about the decorations next. So what is a decoration of complexity K, as defined here? So there are various definitions, and actually what I'm going to describe is something that is not exactly the definition that's needed for this structure theorem, but something that is also a fairly simple reduction from the actual definition. So you can allow extra edges within the face, which are allowed to intersect other edges. So initially, you're allowed to actually put new vertices and connect them in various ways to the boundary, but But I'm going to replace these new vertices by edges that connect to the same points, and it's possible to show that this doesn't interfere with recurrence. So the condition of complexity k, when you phrase it in this way, becomes the following. So this is complexity is the maximal number of new edges that connects the two halves. So you separate this face, so you have the cycle, and you separate it in an arbitrary way to two segments, and you have some uniform bound k on the number of edges that connect the two halves. So some of them could connect, so you could have some edges that connect vertices to very far vertices if the face is large, but you can't have too many of those. And we would like to show that this doesn't really hurt the recurrence of the limits. And the idea is to use the relation with electrical networks. And I don't think I have time, even if Mark asks for it, to define everything here. But generally, I'll just say so.
Mark just taught this to me. I don't remember.
So I'll just say a couple of words. So a flow is a function f from the edges, from the directed edges to the reals, and it's anti-symmetric. So you have along each edge, you can think of something flowing either in one direction or the other, and you want it to be preserving at each vertex. So that's flow. And recurrence is equivalent to having no flows with finite energy of a certain type, where the energy of a flow f is the sum over all the edges of f of e squared. So recurrence is equivalent to having no flows with finite energy, with a certain other conditions, but from a point to infinity in the infinite graph. And yes, and what I'm going to do, I'm going to show that if you have a graph which is recurrent, and you decorate a face like that, then it doesn't change, and you have a flow with a finite energy, then also with a decorated flow. I show that if with a decorated flow you have something with a finite energy, then it's also possible to find a graph where you don't have this decoration, but instead you have some more faces inside. You have something planar inside, which doesn't increase the genus, which has also a flow when the energy is multiplied by at most some constant. And once you have this, so the conclusion is that if there was a flow with finite energy in this, then we can also find some graphs which don't have any decorations, and where you can also have flow with energy which is at most some constant times the original, so it's also finite.
But if you decorate many cases, you multiply with the same constant.
So actually we're going to multiply by a constant the contribution to the energy from the edges inside the face. So you have these edges inside, and they contribute something to the sum, and it's only this component that is multiplied by a constant. So yeah, so it's a good point, but it's not a problem. So how do we do this? And I'm going to draw here part of the face and some edges above it. Maybe one more. And the idea is as follows. So the first thing I'm going to try to do is, and I'm actually going to do this, so basically I'm going to replace the green edges by red edges. And if I have a flow on the green edges, I'm going to find a corresponding flow on the red edges. And I need it to have an energy which is at most some constant times the previous one. So the first thing is to do something like that. So I just create green edges passing consecutively at all the endpoints of the green edges. So there was also one here. Yeah. And I'm going to start rerouting the flow from the green edges to the red edges. So how do I do this? So in this case, it's very easy. I have a green edge and I also have a red edge, so I can just pass the flow from the green edge to the red edge. In this case, I have a green edge which spans two red edges. Okay, so what I'm going to do, I'm going to pass the flow from this green edge onto these two, and it's just going to flow through both of them, one after the other. And in fact, I would like to do this for all of the edges, but that's not going to quite work, because if I have a long edge like that and I pass the flow through many edges, then I get some f. So if I have this edge E and I have f of E squared in the green energy, but in the red energy I'm going to have it many, many times, since there's no bound on the length. So what I'm going to do this only, so I project the flow of short edges to the red ones. So short means that they have length at most 3 times k. So if they have at most 3k red arcs, then I do this projection. Now each of the long edges is going to be projected onto a bounded number of the red ones. So its contribution to the energy is not going to grow by more than a constant. Now there is also some additional things, because you have some of the red edges that get a projection from several of the green edges that pass above them. So in this case you have something like f of e, like sum of f of ei, and you do the square of that to get the contribution from a red edge to the flow. Okay, but this is at most, so if you have a sum, I goes from 1 up to L, so this is at most L times the sum of f of ei squared. So the fact that you get these compound flows on the red edges gives you a factor of at most L, where L is the number of edges that are projected into any red edge. But I know that I have at most k of them, because I assume that the complexity is at most k, so I can't have too many edges connecting this side to this side. So, okay, so this shows that a step of projection like that doesn't increase the total energy by more than a constant factor. The problem is that I'm left with some of the long edges. So let's see where. So let's say that these are some of the endpoints that I still have left.
Why are you worried about the long edges here? I mean, if every red edge is contained in at most L of the original green edges.
Okay, so the long edges are, the thing is that the long edges still have some flow on them. The edges of length greater than 3k.
For all edges. If you do the projection for all edges,
then
red one gets.
Then it's possible that you have some edge like that, and it's going to be projected onto a huge number of edges, and
each one gets a bounded contribution, but that's not.
So if there is a large flow along this edge, then it's going to be counted many, many times after the projection. So you can only project edges up to a certain length. Okay, so let's say I've done this, and what I'm going to do now, I look at the endpoints of the edges that still remain, and I would like to create some more edges. So I create a second layer of edges, of red edges, that span only the long green edges. Now, the thing is that if you have an edge if you have some green edge which is of length greater, which is large, then you can't have too many things coming into it from this side or coming into it from this side because of the complexity. You can have at most k on each side, and this means that in the new setup it's going to be shorter. And in fact, and then I just repeat. So edges that use at most 3k of the new red arches I project, and the ones that are left I keep for the next stage, and I continue like that until everything is exhausted. So how do I know that things will be exhausted? Well, again, so you can have, how many red edges can you have above a given point? Well, you can have at most k red edges above a given point. So after k iterations because each time you will necessarily project something onto every green edge, onto every red edge. So this process is guaranteed to stop after at most k steps, and we get a new graph. Now, as you can see, the red edges don't violate the planarity. So if this is part of a large face, then you can take all the red edges and you still have something which is planar. And this means that we could also apply the original result to that. So that's about the decoration, and I don't have time to speak about the ways that different components can come together. Thank you.
Instead of flows or finite two energy, one could ask about other energies. Do you know anything beyond L2?
Well, okay, so I suspect most of what we've done, I think, will also hold for other energies. So this, for example, has no problem with other energies, and this, and
Z2 is pretty, right? So you can't do any power loss because already Z2 is critical for exactly.
Yes.
You could do logarithmic changes in the gauge.
yes,
Maybe that's too technical for.
So I guess so I think that so without committing, I think that most of what we do in this work will apply, but the original case of planar graphs might be the problematic one.
Shift all the problematic stuff.
And
They're to blame for the fact that
yeah, and for that case, yes, and in that case, I've never thought about trying other functions in the planar case. It's a good question.